All right, rational inequalities. Rational inequalities have some similarities to polynomial inequalities in that if we're going to say where is this function greater than or equal to zero, part of that is knowing where it's equal to zero, right? So we need the zeros of this function, okay? But some of the unique characteristics of rational functions are the existence of vertical and horizontal asymptotes. And those are going to play a part in this. So when you've seen asymptotic behavior in some of these rational functions, right, you see this behavior where as you approach an asymptote, the function may go like this, okay? And let's say, just for the sake of example, the x-axis is here. So this graph goes like so, and then it dips down here and starts going like this, right? So when you see that sort of stop and start at a vertical asymptote, it out of nowhere, a rational functions graph can change where it's located as it approaches an asymptote. So long story short, when we were doing polynomial inequalities, okay, when we were doing these, we always took the domain and we broke the domain up, right, by its zeros. So I don't want to erase that. We broke the domain up with its zeros, and we said, well, it's either going to dip below or be above the x-axis at these points. Okay, we have to be cognizant in a rational inequality of where the vertical asymptotes are. Okay, so these are the two characteristics of this graph that we're looking for. Okay, and for good measure, we're also going to figure out where the holes are and where the horizontal asymptotes are. And at this point, we should be fairly skilled in that. Let's do the horizontal asymptote first, because we always, in case you've forgotten, we always want to do that from the original function, right, based on the degrees. So on the top, we have a 1. On the bottom, we have a 2. So anytime you have a greater degree in the denominator than in the top, our horizontal asymptote is y equals 0. So we already know that we're going to have a horizontal asymptote here, okay? And then for the vertical asymptote and the holes in the graph and the zeros and yada, 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 that was always easier when we had the factored form of this function. The denominator is the difference of squares, which factors into conjugates. The numerator cannot be factored, so we end up with this. Okay, now from here, we know nothing's going to cancel, right? We're looking for factors in the bottom or the top that cancel to find those holes in the graph. We don't have any, okay? So there are no holes, but this does mean that our vertical asymptotes are at +2 and -2 because those values still remain. So we'll put our vertical asymptotes in here at +and -2, like so. All right, I hope you're still with me on that. Now, as far as zeros, where does this function cross the x-axis? The x-intercept, the zero of a rational function is the zero of the numerator. So we want to know where is the numerator equal to 0. And if we solve this, we get 1.5 or 3/2, right? So we know that this function crosses the x-axis at 1.5, right? Which was, if this is 2, 1.5 is about right here. All right, and again, we had a very brief discussion that horizontal asymptotes can be intersected. We've talked about this, provided it occurs close to the origin. Remember that as we move out towards the asymptote, towards the infinities, the graph will approach but not cross the horizontal asymptote. Okay, just for good measure too, while we're here, why don't we find the y-intercept? Okay, the y-intercept is the value of y when x is 0, right? So make this 0. See you later. Make this 0. See you later. We get -3 over -4, which is 3/4, right? +3/4. So we'll put that here. Okay. So we've got a lot of information here. Something that we did not emphasize a lot when we were discussing rational functions is the concept of branches of a rational function. Okay. A rational function, you'll want to write this down. I'm going to say it, but I'm not going to write it. A rational function will have as many branches as its asymptotes. So when I have 3 asymptotes, a horizontal and 2 vertical asymptotes, that means I'm going to have 3 quote unquote branches or pieces to this rational function. Okay. One of them is going to be over here on the left side of this asymptote. One of them is going to be in between these two vertical asymptotes, and the other one's going to be somewhere over here. Okay. And now how that graph behaves, we don't necessarily know without graphing it. Okay. But here's what we do know. And let's do this. We said from the beginning, we're trying to do this rational inequality. So let's take the domain, which would be from negative infinity to -2. Start with that interval. The next interval goes from -2 to the 0. Now the 0 here, right? We're using the zeros and we're using the vertical asymptotes. So 3.5, I'm putting 3.5 here, right? The next one is from that 0 to the next vertical asymptote, okay? And then the final one is from that vertical asymptote to infinity. So the intervals that we use, we have to break it up using asymptotes and zeros. All right. And then so that I don't have to keep going back and forth, I'm just going to use this as my home base for figuring out whether we're getting positive or negative values from this. Okay. So let's start. Let's pick a number over here. We've done this before. Let's scale it back and just go to -1,000 instead of -1,000,000 this time. If I put -1,000 here, I'm going to get a very big negative number on the top. If I put -1,000 in here and I square it, that's now positive. So I'm getting a positive number here. So the numerator is negative, the denominator is positive, which means this is less than 0. What do we want? We want to know where it's greater than 0. So we're not using this interval in our solution set. Now let's pick a number between -2 and 3.5. Okay. The easiest number between -2, 3.5, 3 halves, I'm sorry, 1.5. The easiest number between -2 and 3 halves, if you ask me, that would be 0. And if I plug in 0 here, okay, we already saw what happens. We know what the value is at 0. It's the Y-intercept, right? What's the Y-intercept? +3/4. So this is greater than 0. Check mark. Now, the difference, and you want to be careful here because the difference with rational functions is you can get to an asymptote and a 0 and have that interval. It's not, you might not necessarily see this alternate behavior every time. Okay, so just be careful with that. It's not like it was with the polynomial inequalities. Okay, now let's pick a number between 1.5 and 2. This is where it gets a little weird because I don't have any easy numbers to work with. Okay, but if I do, let's say 1.75, okay, if I plug in 1.75 and double that, that's going to be bigger than 3. And that number that's bigger than 3 minus 3 is going to be positive. But if I square 1.75, squaring 1.75 here is not going to get me all the way to 4, right? That's going to be less than 4. And I'm subtracting 4 from that. That's going to be negative. So I know this is going to be negative, which I don't want. Okay. And then for any value, forgot that there, for any value in this interval, let's say 1,000, okay, what happens when I plug in 1,000 here? I get 2,000 minus 3, that's a positive number. 1,000 squared minus 4, also a positive number. So this is going to be greater than 0. So I am using the values in this interval. Okay, so our overall solution set will go from -2 to 3.5, and I believe we're using, right? We can't use -2, right? Here's a hiccup. Normally I would say, well, there's a line here, right? And this is what we did with polynomial inequalities, right? If there's a line here, that means we want to include the value. But what is -2? -2 is this vertical asymptote. So regardless, I can't use this number in this solution set. I can use the 3 halves because there is a point here, right? So we're going to have to use parentheses at a vertical asymptote, even if we have an inequality with that line underneath it. Okay, and then over here we would again have to use that. All right, let's take a look at this graph. Okay, so here you can see, right, just to verify, what did we say our solution set was? From -2, right? Here's -2. We can see that that graph is clearly above the x-axis until we get to 1.5, which is where it dips below. And then we start again at 2 because we see that asymptotic behavior, that alternating, that dip where one goes super fast decline and one comes from the very top of the graph down. And we see that a lot at these vertical asymptotes, right? That's that asymptotic behavior. So that's why we have to we can't include from 1.5 to 2, but then we do start on the other side of that. And this graph is not going to go back to crossing the x-axis no matter how far out I go. Okay, the y-coordinate is still greater than 0 as we move out towards those infinities. All right, so the graph confirms what we did here. All right.